So we want to look at series and parallel connection of capacitors. So let's take the first one now. Capacitors in series. When capacitors are connected in series, they look in this manner. Now, one thing I want you to know about capacitors in series is that the same charge flows across the capacitor. So the charge in capacitor 1 with the charge in capacitor 2, the charge in capacitor 3 is exactly the same thing. Another thing you need to know is that the voltage across each capacitor varies, except if the value of C1 is same as value of C2 and value of C3. So if their capacitance are the same, then the voltage, but if not, the voltage will divide. So whatever the EMF of the source is, if there is 10 volts, they will share it. Maybe some will take 5, some will take 3, some will take 2, stuff like that, depending on their capacitance actually. So I'm trying to say the capacitor, the voltage across each capacitor is not necessarily the same, except when their capacitance are all the same. C1, the value of C1 and value of C2 and value of C3 is the same. Now, for capacitance in series, the total capacitance is given as 1 over total capacitance is equal to 1 over capacitance 1 over 1 over capacitance of the second capacitor and 1 over capacitance of the third capacitor. Let's take an example now. Two capacitors of 2 microfarad and 4 microfarad are connected in series to a 12 volts. Find the charge on each capacitor and the potential difference across each capacitor. So let's take this question. What are we given? We are given C1, which is 2 microfarad. We are given C2, which is 4 microfarad. And we are given our voltage, which is 12 volts. Now we can say that 1 over C total is equal to 1 over C1 plus 1 over C2, since they are connected in series. So we can say 1 over C total is equal to 1 over 2 plus 1 over 4. The SCM will just be 4. 2 in 4 is 2 times 1, 2 plus 4 in 4 is 1 times 1, 1. So this is just give us 1 over C total is equal to 3 over 4. You can invert this. This will be C total over 1 is equal to 4 over 3. Then put your microfarad, because they all have their microfarad capacitors. So I've gotten the total capacitance. Now we have to get the charge on each capacitor. Well, quite an easy thing. We know that capacitance is equal to charge over voltage. So in this case now, our charge, if we cross multiply this, we give us Q is equal to C. That's our C total actually times Q. C total times Q times V, sorry. Then what's our C total? We've gotten that 4 over 3 times 10 raised to the power minus 6 times, what's our voltage? We're given 12. 3 here 1, 3 in 12 will give us 4. This 1.6 times 10 raised to the power minus 5 coulomb. We've gotten the charge, and that's the total charge, or the charge on each capacitor, or charge in the whole connection. Now the next thing is to get the potential difference across each capacitor. So let's get it. Let's say the potential difference across the first one is V1. Potential difference across the second one is V2. How do we not get that? Let's say we're looking for V1, which is PD across the 2 microfarad capacitor. We all know that C is equal to Q over V. Hence, we can say that V is equal to Q over C. So, what is the Q? The Q is the charge, which is 1.6 times 10 raised to the power minus 5 all over. What is the capacitance of the first capacitor? That is 2 microfarad now. 2 times 10 raised to the power minus 6. So if we do this, we are going to get 8 volts. That's for the 2 microfarad. For the second one now, let's get its voltage. So V2, we call it PD across 4 microfarad capacitor. And so let's get the voltage now. We know that, again, V2 will be Q over C2. What's the Q now? So I should call this V1 and this is C1. So our Q, we've gotten our Q to be 1.6 times 10 raised to the power minus 5 all over. The C2 we have is 4 microfarad, 4 times 10 raised to the power minus 6. If we do this, we get 4 volts. Example 2, 3 capacitors of 3 microfarad, 6 microfarad, and 12 microfarad are connected in series to a 350 volt supply. Calculate the equivalent capacitance and the charge on each capacitor. So let's write out what we are given now. We are given 3 capacitors. C1 is 3 microfarad. C2 is 6 microfarad. And C3 is 12 microfarad. And then we know that we are told that 1 over C total, with the formula 1 over C1 plus 1 over C2 plus 1 over C3. Hence, we can now say that 1 over C total is equal to 1 over 3 plus 1 over 6 plus 1 over 12. The SCM here is 12. 3 in 12 is 4 times 1, that's 4. Plus 6 in 12, 2 times 1, 2. Plus 12 in 12, 1 times 1, that's 1. Over 1 over C total. So this becomes 1 over C total is equal to 7 over 12. You can invert this. This will be C total over 1 is equal to 12 over 7. So turn this upside down, turn this upside down, that's what I mean. So now put your microfarad. Microfarad. We are done with that. Now the second one now, B. The charge on each capacitor. Well, we know that C is Q over V. Hence, Q is CV. Now, what is our C? We are giving our V. We didn't include that here. Our V is 350 volts. So we are giving our C, total capacitance actually. Total capacitance here is 12 over 7. Then times 10 raised to the power minus 6. Don't forget that, micro. Then times your V. The voltage is 350. So this will be 50 times this. Will give you 6 times 10 raised to the power minus 4 coulomb. So this is the total charge, and it's still is charge on each capacitor. The charge on each of them will be the same thing. So that's the charge, and that's that for this question. Capacitors in parallel. Here we have 3 capacitors in parallel. One thing to note about capacitors in parallel is that the charge in the circuit splits across the 3 capacitors. And so to get the total charge, it is the charge on the first capacitor plus charge on the second capacitor plus charge on the third capacitor. Another thing to note is that the total capacitance is gotten by adding the first capacitor, the second capacitor to the third capacitor. Now, the voltage across each capacitor in parallel are exactly the same. So what I mean is this. You see this voltage here, that's the voltage in this capacitor, that's the voltage in this capacitor, that's the voltage in this capacitor. So voltage in the 3 capacitors is exactly the same as the voltage of the circuit. Now, take note, let's solve this example now. That example 3, capacitors of 1 microfarad, 3 microfarad, 5 microfarad, and 6 microfarad are connected in parallel to a direct voltage supply of 100 volts. Let's take out what we are given now. The given here is C1, 1 microfarad, C2, 3 microfarad, C3, 5 microfarad, C4, 6 microfarad. And lastly, we are given the voltage, 100 volts. That means the equivalent circuit capacitor. So let's take the first one now. We can say total capacitance is C1 plus C2 plus C3 plus C4. 1 plus 3 plus 5 plus 6. 15 microfarad capacitor. B, the total charge. We know that capacitance is Q over V. So we're looking for Q now. Q will be equal to total capacitance times the voltage. Total capacitance is given as 15 times 10 raised to the power minus 6, which is what we got here, times the voltage 100. So this will give us 1.5 times 10 raised to the power minus 3 coulomb. Now the C, the charge on each capacitor. The charge on each capacitor will be Q. Let's take for C1, we have that Q1 will be equal to, so C1, the first capacitor, the charge on it will be C1 times V, which is simply be, our C1 is given as 1 times 10 raised to the power minus 6, then times 100. That will just be 1 times 10 raised to the power minus 4 volts. For C2, that's Q2, which is C2 times V. And we have that our C2 is given us 3 times 10 raised to the power minus 6 times 100. And that will simply be given 3 times 10 raised to the power minus 4 volts. For C3, we have it that Q3 would be given as C3 times V, which would also be, our C3 is 5 times 10 raised to the power minus 6 times 100. And this will be 5 times 10 raised to the power minus 4 farad. Again, for C4, the fourth capacitor, we have that Q4. So Q4 is the charge on that capacitor, and that's given as 6 times 10 raised to the power minus 4 times 100. And that will give us 6 times 10 raised to minus 6, sorry. So 6 times 10 raised to the power minus 4 volts. So that's that for this question. Discharging a capacitor. A capacitor which is charged to a potential difference V0 can be discharged through a high resistance, as we can see in the circuit below. So this is how the circuit diagram is while discharging a capacitor. It's important to know that there's a relationship for the voltage, current, and charge in that capacitor after being discharged. Actually, for a time t, or after a time t, we have it that the charge in the capacitor is equal to the initial charge exponential minus t over tau, which is time constant. And that the voltage as well will be equal to V0 exponential minus t over tau, which is time constant as well. Or the current is equal to I0 exponential minus t over tau, which is time constant. Let's define time constant. You see, time constant measures how fastly the capacitor charges or discharges. It is the time taken for a capacitor to charge or discharge to about 63% of its final value. Now, the time constant is given as resistance times capacitance, actually. The capacitance of the capacitor times the resistance of the resistor. Example 1. A capacitor is discharged through a 10 mega ohm resistor and it's found that the time constant is 200 seconds. Calculate the value of the capacitor. So here now, we are looking for the capacitance of the capacitor. So we are given that our R is 10 mega ohm, which is 10 times 10 raised to 6 ohm. Again, we are given the time constant to be 200 seconds. Now, we have the time constant is equal to RC. So we can say C itself is equal to tau over R. So our tau is given as 200 over our time constant 10 times 10 raised to the power minus 6. 10 raised to the power 6, sorry. So this will simply give us 2 times 10 raised to the power minus 5 farad. Calculate the time taken for the potential difference across a 100 microfarad capacitor to fall to 80% of its original value if it is discharged through a 20 kilo ohm resistor. Let's solve this question now. This is our example 2. So what are we given here? Firstly, we are told that we are looking for time, okay? And then taking for the potential difference across a 100 microfarad capacitor. So we are giving the capacitance of the capacitor to be 100 times 10 raised to the power minus 6 farad to fall to 80% of its original value. So it means that the V fell, we are using this equation to fall to 80% of its initial value. The initial value of the voltage is called V naught. So we can say this is V is equal to 80 over 100 V naught, which is same as 0.8 V naught. Now, we are given the resistance of the capacitor. The R is given as 20 times 10 raised to the power 3 ohms. That is kilo ohms. Now, let's go now. What relationship am I using? I'm using the voltage relationship because we are asked to calculate the potential difference. If the equation says calculate time taken for the current, I'll use the current equation. If it says calculate time taken for the charge, I'll use the charge equation. So this will be V is equal to V naught exponential minus T over tau. Now, the first thing we need to go and do now is to calculate our tau. Remember, but tau is equal to R times C. Our R here is 20 times 10 raised to the power 3 times 100 times 10 raised to the power minus 6. This will just give us 2 seconds. That's our time constant. Now, since we have our time constant now, we can go ahead using this relationship. But we know our V is 0.8 V naught. So I'll put 0.8 V naught here. 0.8 V naught is equal to V naught, then exponential minus T over tau, which is 2. So the question says we should find time. So this is the time I'm looking for here. First of all, V naught cancel out V naught. So we have 0.8 is equal to exponential minus T over 2. Next thing we do is to take ln of both sides, natural log of both sides. Ln of 0.8 is equal to ln of exponential minus T over 2. And that's because ln, we take out this exponential. And that will give us minus T over 2. That was left here. If we take ln of 0.8, let me quickly do that. Ln of 0.8, we have minus 2.23. Sorry, minus 0.223. Then now we can eliminate the negative and then cross multiply. This will give us T is equal to 2 times 0.223, which is 0.446 seconds. That's the time we are asked to get. That is